Our subject code is CEC358 Underwater Imaging Systems and Image Processing. So in this unit 2 is about optical image processing. So and the topics under unit 2 are given here. So in this video we are going to discuss about image segmentation, pattern recognition and challenges involved in underwater imaging. First we will see about image segmentation. So as we all know, segmentation is nothing but dividing an image into regions that are connected and have some similarity within the region and some difference between the adjacent regions. So our goal is to find individual objects in an image. So what are all the individual objects in the image? So how we can find the individual objects? For that we have two approaches. One is discontinuity and another one is similarity. So similarity may be due to the pixel intensity or color or texture. So how will we find the discontinuity? The differences or the sudden changes that we call as discontinuities. So in that case we can find the sudden changes in the intensity along the boundary line, which we call as an edge. So let us start with the finding of discontinuities. So one is to find the similarities and another one is to find the discontinuities. So let us start with the approach of determining the discontinuities. So we can find three different types of discontinuities in intensity. So first one is points, next one is lines and another one is edges. First we will start with the point detection. So for any discontinuities we have to define a mask. So the mask can be maybe a 3x3 matrix or 5x5 like that. So let us take the pixel values, the mask values to be W1, W2, W3 etc. up to Wn. Now we have to find a mathematical operation for this. So the image gray values to be multiplied with the mask values. For example, if you take Z1, Z2, Z3 up to Z9 are the gray values of an image of a particular area in an image, then if we place the mask coefficients and we have to apply this particular operator, then you find the value of R. By finding the value of R, and you have to fix a threshold value and compare that value with the threshold value, where T represents a non-negative threshold. So the mask may be like this. So by finding this mathematical operator and comparing it with the threshold value, then we can find if there is any change in the discontinuities, that is any abrupt values, very peak values that we can able to find out. So now let us start with the point detection. Okay, similarly, so if it is at one point, then we can call it as a point detection. So here we are finding the value of R and we are comparing it with the threshold, and if the condition is, that is the modulus of R is greater than or equal to threshold, then we can find it as a discontinuity. Next we will go to the line detection. So in detection of discontinuities we have point detection, line detection. Okay, first we complete point detection. What is line detection? So here also the mask is like this. So in the point detection you see the mask only one pixel is different from its neighbors. But here in line detection you see for the horizontal line how it is, for the vertical line you see the mask. So for the horizontal line the mask is like this. For plus 45 degree the center pixel you see it is 2, 2, 2, and for vertical it is the center pixel you see 2, 2, 2, and for minus 45 the diagonal is like this. So by placing this mask over the image and finding out the coefficients multiplied with the image gray values, we are finding one value and we are comparing it with the threshold. Now you see this figure. So what is this figure? We are seeing the first figure A represents the binary wire bond mask. So next B value represents the absolute value, that is we are finding this with the minus 45 line detector. You see this minus 45 line detector, fourth mask. So it is like this. So by placing this mask we can find out these lines in this image. And for what is C figure, this below figure, what it represents? It is the result of thresholding of image B. So by comparing this with the threshold, only 45 lines will be present here. Okay. So next we will go for edge detection. Point detection over, line detection over. Next we are seeing the edge detection. So how to find the edge detection? So this we are actually modeling an ideal digital image. So edge, what is an edge? It is an abrupt change in the intensity value. For example, if you take your face, consider your face is having the skin color will be bright, but the hair color will be very dark. So there is a point, or there is an edge which differentiates between the skin color from the hair color. Similarly, you see this image, here we are having black color. So it has one gray profile, that is very low profile, but this gray color is having a high profile. But here in the second figure, if you see, it is a model of a ramp edge. If the edge is like this, like you have some transitions, then we have the gray profile like this, slightly increasing towards the brighter side. So the graph also, it is increasing towards the higher side. How we will find the edge detection? So this is the same structure, but here if it is very bright point in the C figure, if you look at, so it is having some roof edge also. Okay, next we will see the edge detection. You have this value. So actually difference, edge detection, how we are finding the discontinuities means it is the difference in the intensity value. So if we find the difference with the neighboring pixel once, only one difference if you are taking, then we call it is a first derivative. If you are taking 2 times the difference between the 2 neighboring pixels, then we have that to be a second derivative. So how you see the figure, it will be very clear for you. So this is actually the transition between the black and the gray color, and this area is projected here. So here the center point is nothing but the transition from the black to white. So it the graph also, it goes from the lower end to the upper end, and in this transition profile, if you take the difference value, then it is constant for the first derivative, but in the second derivative, if you see, you have only the edge points. It is the positive line and this is the negative line. So this is the same as we are discussing here. Why there is some changes in this graph? It represents some noise. The signal is corrupted by some Gaussian noise. Next we will see the gradient operator, because the difference means we have to take the gradient operator. If it is single difference, then it is gradient, and if for second derivative 2 times if you are taking the difference, then it is Laplacian operator. So first order derivative, this is already we have discussed. So what is the del operator with respect to the x value? If you are finding the difference with the x axis, then it is dou f by dou x. If you are finding the difference of the pixel with the vertical axis, y axis, then it is dou f by dou y. So we have to find the magnitude by this formula and direction by this formula. So if there is any greater change in the difference, then we can say it is an edge. The edge is deducted. Similarly, you take this figure. So here gradient means single operator. This is the first figure represents a particular pixel. So from this particular pixel, you are going to take a difference with the x axis and also with the y axis. Here the alpha represents the edge, with what angle it is tilted, the difference is deducted. So the difference in the intensity value determines it is an edge. So similarly, in this single first derivative operator, we have three types of mask. So one is we call as Roberts cross gradient operator. You see the mask it here. Since it is a cross gradient operator, you see along the diagonals it is like this. Since it is a difference operator, gradient is a difference operator. If you sum all the coefficients in a mask, it will gives you the net value as 0 in all the, either it is a Roberts cross gradient or Prewitt operators or Sobel operators, whatever it may be. If you sum up all the coefficients in a mask, the net value will be equal to 0. So from ordinary masks, so far we have discussed in filters also, averaging filters, weighted average, whatever, it is not so. But in the difference operator, difference mask, you can find this changes. So this Robert is it's also an edge deductor. So these three marks are very famous marks for finding out the edges. So this is cross gradient. It is to find out the diagonal elements, and this Prewitt operator is nothing but to find the horizontal and the vertical edges. And this Sobel operator, we can also find out the horizontal and the vertical edges. So how this is for the next diagonal edges. This Prewitt mask and Sobel mask we can also have for diagonal edges also. So you see the figure in illustration here, this is shown in the figure. So the first figure represents the original image and second figure represents the gradient component in the x direction. You see the horizontal lines only, we have the gradient operator, that is the difference operator we are finding. What are all the edges differences in the horizontal that we are seeing. And C figure, it represents the y direction only. You see the lines, the windows or everything, the vertical lines, edges are deducted. And in the fourth figure you see sum of the gradient image, that is x and y. If you add these two, then we get all the edges, either horizontal edges and vertical edges, all edges we are obtained in the fourth figure. So thus the deduction, edge deduction is obtained with the help of gradient operator, that is differential operator. So this is another one example that you can go through it. So next we will see second order derivatives, that is Laplacian operators. If you are taking the difference in both of your neighbors, from both of your neighbors, actually you are sitting in the center, means you are taking first difference from your left neighbor and you are again taking the difference from the right neighbor also. So if you are taking 2 times difference, then we can say it is a second order derivative. So always a second difference, 2 times the difference, we call that as a Laplacian. If it is a single derivative, first order derivative, we call that as a gradient operator. So and the del square f is difference, it is given by this formula. So and the mask is also like this. Here also if you sum up all the coefficients in a mask, you will be getting a net value to be 0. So this is the Laplacian mask and it is different from the gradient mask, that is single derivative. But here you have to take both the here you consider the 4 to be the center pixel. You have to consider both the left neighbor and right neighbor, that is in the x direction, and for the up and down neighbors also in the y direction. So it is like this. So also we can have more advanced technique for edge deductions also, and this Marr-Hildreth edge deductor is a famous advanced technique. So here I will mention only the highlighted points of this edge deduction. So this intensity changes are dependent of image scale only, and so the deduction requires the use of operators of different sizes, and that a sudden intensity change will give rise to a peak in the first derivative and equally to 0 crossing in the second derivative. So this is the highlighted point where there is an intensity change, means so it is in the first derivative peak. You see the first derivative value in the graph we are discussed. So this figure, so in the first derivative, so it is in the peak value, and in the second derivative whenever there is a 0 crossing, there is a changes in the second derivative. But here it is of constant edges in the first derivative. So now if you see the there is a peak in the first derivative and equally to 0 crossing in the second derivative. Next, what are the 2 important feature of this Hildreth edge deductor are, it should be differential operator. First, if it is a edge deduction, definitely we have to use the differential operator, because the difference in the intensity we have to find out, that is our goal. So we have to use a differential operator that should be capable of computing the first derivative as well as the second order derivative at every point in an image. So our differential operator should capable of computing both first order and second order derivative. What is the second important feature? It should be capable of being tuned to act at any desired scale. So whether the image may be of small scale or big scale, if you multiply with any size, then also the capable, that operator should be capable to act at any desired scale, so that large operator can be used to deduct blurry edges, as well as a small operator is able to deduct the sharply focused fine details. So all these features are incorporated, so we can call this as an advanced technique. And here also we are finding the first order derivative of g of x and 2 times derivative, then we call this as a Laplacian derivative. So finally we can call this as a Laplacian of Gaussian. So this particular operator, this differential operator is combined the important salient features. So it is able to deduct all the types of edges, even the blurry edges as well as the fine details we can able to find out. So you see this figure, it is also an example for this Hildreth operator. So here also you see this figure. So okay, A, B, C, D. What is this A figure? It represents the X-ray image, that is the bone of image, and second figure represents the Sobel gradient. So where all the lines, the changes in the intensity, that we call it as an edge. So the edge lines are marked. And this third function we call as a Gaussian smoothening function. Smoothening means some blurring effect will be produced in the image. And finally we are using the Laplacian mask also. Some gradient function, Laplacian of Gaussian, that is Hildreth operator is an advanced edge deduction techniques. It applies two difference operator. One is the Gaussian smoothening function and another one is the Laplacian mask we are using. So by applying this we can able to find out. Okay. So first represents in the before figure, it represents the original image. But here this image, this first E image, it represents the Laplacian of Gaussian operator. Next, this second box, it represents the threshold value. So threshold means always it gives only the output two intensities, either black or white. So we can call this as a binary image also. What is a binary image? It contains only two intensity values. So either 0 or 1, that is binary. Okay, so this binary image, it is the threshold of this Laplacian of Gaussian operator. And what is this last figure? It represents the zero crossings. So, okay, so all this, it is very evident. By applying this, what can we get? So next is an important topic in segmentation, that is how transforms. This how transforms takes the images created by the edge deduction operators. So what is this transforms takes? It takes the images created by the edge deduction operators. Most of the time, the edge map generated by the edge deduction algorithms are disconnected. Why we are going for Huff transforms? Because the edge deduction outputs are disconnected. The lines are disconnected. So this transform can be used to connect the disjointed edge points. That edges has to be connected. So for that we are applying this Huff transforms. It is used to fit the points as the plane curves. So the plane curves may be circles, lines, parabolas, anything. So on the line equation, generally we know y equal to mx plus c. However, the problem is that there are infinite line passing through one points. Okay, and this is the slope and intercept of this line equation that we all know. And this is the Huff transform, and the algorithm is given below. So how the edge points are connected, how the connection is making through this, that is the detailed step and very clear also it is given here, and we can use these steps to find out the algorithm. So only we have 7 steps and that has to be repeated. So by applying that algorithm Huff transform, we can connect the edges. So okay, the disconnected edges can also be connected. So in the first you see Huff transform, a way of finding the edge points in an image that lie along a straight line. So one is if it is a straight line or curves or circles, we can able to find out. So for to find a straight line, we have to apply this equation. So okay, next we can also find this all the pairs. So that detailed steps is given below. So that is the output of the Huff transform. It is obtained like this. So next method. So we are in the discontinuities. We have two approaches in the segmentation. First approach is to find out the discontinuities. In the discontinuities itself, we have 3 types. One is point deduction, line deduction, and third one is edge deduction. In the edge deduction also, we have discussed so many types. Differential operators, 2 differential operators we had discussed. And in the edge deduction, the outputs, that is the edges are disconnected. So for that we are using the Huff transform, and that detailed steps is also discussed. Now we are going to with the next method, that is thresholding. So here nothing but you have to range the intensity levels that is covered by the objects of interest in different from the background. How it is different from the background, that you have to obtain. So first you are applying single threshold. So you are classifying, you see the intensity values, it is less than threshold or above threshold. Like that you are classifying all the intensities in the image. In the second figure you see we are taking multiple thresholds. So in this case we are taking 2 thresholds, T1 and T2. So what are all the intensity values lying below T1, lying above T2, and in between T1 and T2, that we are differentiating all the values. So this is also one type of deduction, okay, edge deduction only. So you see in the case of illumination, what is the illumination plays the role. So here in the first figure, you take the reflectance function. It is a computer generated reflectance function. For that, if you produce a histogram of this first image, we get like this. So histogram, we know it is the range of intensities present in an image. So here we have only two intensities. One is the black and another one is the gray profile. So the black means it is most of the intensities are in the black intensity. So it is the first curve you see in the second graph. The first curve represents the black intensity and the last curve represents the white or the gray profile intensities. So this is the role of illumination. So you see the figure, we can able to understand. So the first component is the reflectance component and second component is the illumination component. And you see the third figure, this D figure, what it represents? It is the both illumination component and reflectance component. Now if you see the histogram, we can get the product image of the histogram. So that is illumination. If you add the illumination components, then we get the histogram like this. So similarly, what is this thresholding operation? You see the image. So first figure represents the original image and second one is the histogram image. So for this we have also two profiles. So we have this black color in the near zero intensities, and near high values we get the white color intensities. And after thresholding, what that is the global thresholding. What is global means, if you are applying the thresholding procedure to the overall image, then it is called global. If you are applying to any one part of a image, then we call that is a local thresholding. So here we are applying, after applying global thresholding, we get the output like this. So okay, this is next one example. Similarly, we can go through that. So here it is the original image and second one is the histogram of the image and third one is the segmentation. How we are segmenting. This is one intensity and the background we are separating. So okay, in thresholding we are differentiating the background from the foreground images. So here also it is adaptive thresholding. Okay, it is not fixed. The threshold value is not fixed. So it is accordingly changes with the image value of the intensity. So that is we call as adaptive thresholding. So we can also use optimal global and adaptive thresholding according to the application where we need. So if you have a certain fixed intensity, there we can use a global thresholding. But if the image intensities are abruptly changing everywhere, there we can use this adaptive thresholding. So and using thresholding, we can also obtain the boundary characteristics. You see this example, it is very clear that we are actually separating foreground, the information from then we are eliminating the background information. So this is for the color image. If we apply thresholding, it will looks like this. So next, discontinuities is over. In segmentation, we know that we have two approaches. One is detection of discontinuities and another one is to find similarities. So far we had completed the discontinuities, detection of discontinuities. Now here in region based segmentation, actually we are going to find out the similarities between the pixels. Which pixels are having similar intensities, that we are going to see. So see first one, what is this region based segmentation? Edges and threshold sometimes do not give good results for segmentation. So what is the drawback? So far we are finding the edge detection and discussing about threshold. That won't give good results. So that we are going for region based segmentation. So as we know, it is the aim here. We are able to give the connectivity of similar pixels in a region. So what is the condition to connect to similar pixels? Each region must be uniform. That is the first one. Second condition, connectivity of the pixels within the region is very, very important. There the edges are disconnected, for that we are using half transform. But here we are going to connect the pixels. So there are two main approaches for this region based segmentation. So what are the two approaches? One is region growing and another one is region splitting. So in region based segmentation, this is the general procedure. So how capital R represents the entire image region, and we are going to split the image regions into sub-regions, and we are finding the all the union of all the regions gives the first region. So we are defining the conditions that each sub-unit is a connected region and there is no intersection. Each regions are different. Like that we set some conditions for this region based segmentation. So here first we will discussing about region growing. So thresholding still produces the isolated image. Region growing algorithms works on the principle of similarity. Next point, it states that a region is coherent if all the pixels of that region are homogeneous with respect to some characteristics such as color, intensity, texture or other statistical properties. So when coherent means similar. When two players are coherent, we tell some similarity measures we fix and we find out. Similarly, how we can find out the similarity between the pixels? For that we need some characteristics. The characteristics may be color, anything like that. Thus, the idea is to pick a pixel inside the region of interest and as a starting point, and this point we call as a seed point, and allowing it to grow. So whether the next pixel is also having the same value, then we will connect between these two pixel values. That is the growing procedure. Seed point is compared with its neighbors and if the properties match, they are merged together. So this process is repeated till the regions converge to an extent that no further merging is possible. It is a process of grouping the pixels or subregions to get a bigger region present in an image. Similarly, first what are all the three steps here? Selection of the initial seed. So far we have discussed the same. And second one is the seed growing criteria. And third one we have to, where we have to terminate the process. Similarly, it is shown with an example here also. So what is the seed point and how we are growing and where we are terminating. And this region growing algorithm is slow. So the seed point can be extended to a seed region. So okay, here we are going instead of taking a point, we are going to a region, seed region. Instead of a single pixel, a node of region adjacency graph, that is RAG, that is region itself is now considered to be a starting point. Because very small point, if we want to grow, means it takes more time. So still we will take a region now and we are going to grow that region. Okay, so that is split and merge algorithm. So here the algorithm steps are repeated here. First we have to segment the image into region with the number of thresholds. Then we have to create this regional adjacency graph and using some similarity measure and formulate the homogeneity test. The homogeneity test is designed based on the similarity criteria such as intensity or any image statistics, and we have to repeat this homogeneity test step until no further region exists that require merging. First we have to split the region and then we have to merge the region according to the similarity measure. So since the first one, region growing, is slow, we are going for the split and merge algorithm. So and the procedure is given below. Okay, this is the figure. This is also a segmentation procedure based on region growing. So this illustration we can get very clear idea how this region growing algorithm works. Next, this same split and merge we can also use with a quad tree. So instead of regions RAGE, then here we can use a quad tree. Here the homogeneity test is applied. First we have to, the entire image is assumed to be a single region. Then we have to apply the homogeneity test. If the conditions are not met, then the regions are split into 4 quadrants. So this is the quad tree approach, and this process is repeated for each quadrant until all the regions meet the required homogeneity criteria. If the regions are too small, then the division process is stopped. So here the steps are given, the same steps here. Okay, so region splitting is the opposite of region growing. First there is a large region, then a predicate is used to determine if the region is uniform. If it is not so, then the method requires that the region can be split into another 2 regions. So the process will be continued. So the main problem with the second, that merge, split and merge algorithm, is that where to split a region. That is the problem. How to determine this, where to split a region. So for that we can use one method to divide a region is to use the quad tree structure. So what is a quadtree? It is a tree in which nodes have exactly 4 descendants. So you see this first total image, the area R, it is divided into 4 regions, R1, R2, R3, R4. This first image you see, and this fourth region, R4, is again divided into 4 regions, R41, 42, like this. So this is the same quadtree is described in a tree structure here also. So the same splitting procedure is shown here. Okay, so with this the segmentation is over. Next we will start with pattern recognition. So in pattern recognition we will see the important features. We know pattern recognition is an important branch of artificial intelligence. We know today artificial intelligence is an emerging field. Humans can recognize the faces without worrying about the varying illuminations, because we human, we have such an intelligence, so we can able to recognize the faces. When implementing such a recognition artificially, then it becomes a very complex task. So the field of artificial intelligence had made this complex task possible. Now machines are going to do the recognition feature. So for that we are going with this pattern recognition. What is a pattern? A pattern is a set of objects or phenomena or concepts where the elements of the set are similar to one another in certain ways or aspects. You see these examples, it's having some pattern. So it is an entity that could be given a name. For example, it may be a fingerprint image or DNA sequence, anything. So these are some of the examples: fingerprint, footprint. Okay, so this pattern recognition procedure of processing and diverse information characterizing the objects or phenomenon so as to provide descriptions, identifications, classifications and interpretations. So this is how a machine can perceive, process and predict. So okay, this is nothing but perceive, process and prediction. So for that we have to design a system. What is a recognition system should have? It should follow the 4 steps. First, it has to acquire the data and pre-process the data. Next, it has to represent the data. Third one is feature extraction. Finally, it has to decide, decision making is the last step. So these are all the process here. Data acquisition and sensing process here. First step is acquisition. Next is pre-processing. Okay, what is acquisition? Measurements of physical variables. Number 2 is, and what is the problem with this? The bandwidth, resolution, etc. Second step is pre-processing. After acquiring data, we have to pre-process the data. That is removal of noise and anything, isolation of pattern from its background. After isolating the patterns, we have to find the best features. So third step is feature extraction. For that, finding a new representation in terms of features. And finally is the classification. Using features and learned models, we have to find a pattern, classification. For example, if it is a group of shapes, it is triangles, circles, squares, everything mixed means, then we have to classify all the triangles into one group and squares into one group. That is classification. And fourth one is post processing, that we have to evaluate of confidence in decision, whether our decision is correct or not. So that the same is shown in the flow chart also. And for this model, we can either create a statistical model or syntactic model, template matching model and neural network model. Each model has its own algorithms also. Here also we have to define a class, pattern class. It is a set of patterns showing or sharing the common attributes. So here a collection of similar objects is very important. So during recognition, the given objects are assigned to a prescribed classes. So this is the algorithms, how it train, the system is trained or learning. So classification, how it classifies. So one we have supervised learning and another one is unsupervised learning. So you see the algorithm, it is very clear. In the first step, it is learn about shapes. So the triangles and circles are already classified. The training set is like this. So the system is trained with the different sizes and alterations, rotation of triangles and circles. Next, it is going to a classification. If you are giving a triangle, yes, it is triangle. Next, it is the colors also, we can make the system to learn. But here it is unsupervised learning. Here everything is mixed together. So clustering criteria. Using some similarity measures, the machine itself classifies the triangles from the circles. Okay, so this is unsupervised training and learning. And what are all the applications? Why means that we can see that computer aided diagnosis. So the scans all they are taking now. So defining the pattern already it is fed up with so many inputs. So now if the patient is if the image of a scan image of the patient is taken, it is going to compare with all the trained models, and finally it produces the corresponding results. So this is the design. In the architectural building also we can use this pattern recognition. Science and engineering, there also we can use this. It is used mainly in manufacturing industry, healthcare, military. So character recognition, text characterization, speech recognition, fingerprint recognition, signature recognition, face detection. So many applications this pattern recognition. So in this ECG also we are using this pattern recognition. So okay, and face recognition, eyelids, that is iris, that also we can able to detection. And these are listed. What are all the detailed applications? It is listed in this table. So this conclusion, what we can conclude? So many techniques are there: statistical methods, neural methods, syntactic methods. Each have its own advantages and disadvantages. Okay, with this pattern recognition is over. Next we will move on to the last topic, that is challenges. What are all the challenges we have in the underwater imaging? So we know the sources of underwater images get distorted because of light scattering and color change. So inside the water the image gets distorted because of two factors. One is, these are the challenges actually. One is the light scattering and another one is the color change. This light scattering lowers the visibility and contrast of the captured image. So first what it happens to, if it is light scattering, it lowers the visibility and contrast of the captured image. And second one is the color change. It leads to the varying degrees of attenuation. So different attenuation will happen if there is a color change. You see the image here, it is the undersea image. So here hazing and bluish effect, the color change is also happen. It is caused by the light scattering and the color change. Okay, that hazing effect is there. So to enhance, now how to enhance these features, how this underwater problem can be solved means, it is, there is an algorithm, that is a dehazing, wavelength compensation, image dehazing algorithm is there. We can use that algorithm to overcome the challenges. So dehazing also provides some problem. Okay, so what is this image dehazing? What is a haze actually? Haze is caused by the suspended particles such as sand, minerals in lakes, river and ocean. So they are the suspended particles, and it adds some effects to the image. So capturing image underwater is challenging due to the haze caused by the light. So this is the main challenges we have in the underwater imaging. And this is a simple flowchart of how to overcome. This is one of the point we can add, how to overcome this haze problem. For that we can use this wavelength compensated image dehazing algorithm. This flowchart is given here, but our topic is to see what are all the challenges present in the image watering. So we have to create the image formation model. In this image formation model itself, we have so many challenges. So you see here, it is underwater. This horizontal line separates the illumination source, and this is the underwater region. Here you see so many factors. So in the air light, so here the object and the camera distance, it creates some of the challenges, and the distance between the surface layer to the depth where the object is actually present. For example, if you take a fish inside the sea, what is the depth? So that depth creates some of the image changes in the images. That particles, suspended particles in between the camera and the object, there may be some of the unwanted particles also suspended. So that all it creates a challenges. And this second one, it capital L represents the artificial light source. So all these are challenges, and they have to be modeled accordingly. So this artificial light and camera, the depth, and some of the unwanted objects present between the camera and the object. So the distance. So everything It is a challenging part in this thing, and artificial removal, that artificial light source has to also to be removed. So everything, all these in this model we can see everything is a challenges. So this is how, what are all the effects that we can overcome these challenges. That are some of the few points are discussed, but our topic is list out the challenges in underwater resulting imaging. Okay, this is the advantages of that algorithm. So all the topics so far discussed I am taken from the image processing book, that is by Rafael Gonzalez. Okay, thank you.